Let us continue our course on recurrent neural networks, Chapter 2, Appendix 2. In this section, we introduce the least mean square algorithm. Recall that we have defined a simple recurrent neural network in previous sections. Equations 2.40 to 2.43 define the simple recurrent neural network. Its architecture is shown in this page and next page. In these equations, S_t is the external input sequence and H_t is the activation state. X_t is the internal state, which is a function of the activation state of the previous step, and the external input sequence with weights and biases. The activation state, H_t, is a nonlinear function of X_t. Z_t is the linear layer output, which is a function of H_t. P_t is the nonlinear output through an activation function psi, for example, a softmax function. The least mean square algorithm was initially developed for a single linear neuron, which can easily be expanded to a multi-neuron, a vector, and one may add nonlinearity as well. In this lecture, we will show how the least mean square algorithm can be applied to the simple recurrent neural network. The architecture of the simple RNN is shown in this slide, where the input is S_t and output is P_t. The hyperbolic tangent function is used as the function g, and softmax is used as the function psi. Let us describe the LMS algorithm in the simplest form as a linear mapping of a random vector input to a random scalar output, as shown in equation 2.44. Where the random variable vector s and the parameter vector w are m-dimensional vectors, and x is the random scalar output corresponding to the input s. The transpose of vector w can be viewed as the first row of the matrix W in equation 2.40. The two vectors, s and w, are indexed by k. For each input vector s, the desired label is the scalar y. Let us use the L2 norm squared of the error difference, that is y minus x, as the loss function for the learning phase. The L2 norm squared of y minus x is shown in equation 2.45. By taking the linearity of the expectation function, equation 2.45 can be rewritten as equation 2.46. Furthermore, also using the linearity of the expectation function, we can let the expectation pass through summations, and get the final result shown in equation 2.47. Now, we can apply the stochastic gradient descent to the loss function shown in equation 2.47. We summarize the above equations by using the following steps. 1. Expand the first L2 norm square equation. 2. Use the definition of the linear network. 3. Use the fact that the expectation operator E is linear and thus passes through summations. As a result, the loss function is now a function of 1. The square mean value of the labels, namely, the expectation of y square. 2. The cross-correlation functions between the input elements and the label, that is, the expectation of S_k times y for all k. 3. The autocorrelation functions among the elements of the input signal, that is, the expectation of S_j times S_k for all j and k. To obtain the optimal parameters, that is, the vector w, we first calculate the gradient of the loss function with respect to each element of w, which is shown in equation 2.49. We can also derive the second derivative of the loss function, which is the Hessian matrix, as shown in equation 2.50. There are two approaches in finding the optimal parameters of this one neuron example. Approach 1, set the gradient to 0, and then solve for the optimal parameters. This linear filter gradient system is in fact a convex optimization problem. Thus, the optimal parameters can be obtained by setting the gradient to 0 and solving the equations shown in equation 2.51. But we need to use the second derivative of the loss function, that is the Hessian matrix, to determine if the optimal point is stable, unstable, saddle, or degenerate point. Equation 2.51 can be expressed in the matrix format as shown in equation 2.52. Where the symbol, left bracket 0 right bracket, on the left-hand side of equation 2.52 denotes the m-dimensional vector of zeros. By rearrangement of the variable ESY, we get equation 2.53, which is a linear vector matrix equation in the unknown parameter vector W. Where the expectation of S times its transpose is the symmetric covariance matrix. The expectation of S times Y is the cross-variance of the input vector S with the desired label Y. We notice that equation 2.53 is the Wiener optimal filter, which, if solved, would produce the optimal Wiener filter parameter vector W. The global unique solution to the Wiener filter requires that the covariance matrix be non-singular, that is, it is invertible. Then a unique optimal filter parameter vector WO can be obtained by equation 2.54. If the non-singular covariance is also positive definite, then the solution is the global minimum. Since the covariance is symmetric and symmetric matrices have only real eigenvalues, thus we can conclude that the covariance is positive definite if all the eigenvalues of the covariance are positive. The Wiener optimal filter approach has two challenges. 1. We need to estimate the cross-correlation and autocorrelation without knowledge of the probability densities of the random variables s and y. Recall that s is the input vector and y is the output label. 2. Computing the inverse of a matrix may be computationally intractable. The second approach to find the optimal parameters of our one-neuron example is the method of steepest descent based on the stochastic gradient descent. As shown in equation 2.49, we can define gradient dynamics for the parameters incrementally, as in equation 2.55, where t is the iteration or time index. Iterating this gradient system should lead to the global optimal solution of this convex optimization linear system with a quadratic loss function. This approach eliminated the need for computing the inverse of a matrix. However, the challenge of estimating the expected value of the cross-correlation and autocorrelation still remains. Let us solve the challenge of estimating the expected value of the cross-correlation and autocorrelation by making the following assumption. Let us assume that the input and the corresponding label come from an ergodic process. Based on this assumption, the statistical ensembles can be estimated by the corresponding time averaging. This allows us to use samples over time. That is, we may remove the expectation operator from equation 2.55, which is the dynamic gradient descent. As a consequence, we can settle for time iterations of the dynamics of the parameter vector. This approach is sometimes also referred to as online learning. After removing the expectation operator from equation 2.55, equation 2.55 can be rewritten by equation 2.58, which gives the parameter update equation as shown in equation 2.60. If we view the weight vector as a row vector, that is, taking the transpose of the original weight vector, equation 2.60 can be rewritten as equation 2.61. In general, the parameters of a neural network are a matrix, denoted by W hat. And we have multiple outputs, that is, x is a vector. Then equation 2.61 can be rewritten as equation 2.62. Where now the difference y minus x is an n-dimensional vector. The method of steepest descent can be summarized as a procedure of the following actions. First, initialization. Choose the hyperparameter, which is the learning rate eta. And then initialize the weight matrix W_0 hat with small random element values. Second, forward pass. Pick a sample input S, and run the network to obtain the corresponding output vector X. Third, backward pass. Compute the error vector Y minus X. In our single-layer example, there is no network to pass through backward. Later on, we will see the backpropagation process in multi-layer neural networks. Fourth, update the weight matrix in one step. Or if we want to update in a mini-batch, then we repeat actions 2 and 3 and update over several steps. Fifth, iterate. Go to action 2 for either a pre-specified number of epochs or until the L2 norm of the error vector y minus x becomes below an acceptable level. Let us summarize this chapter. In essence, it makes the effective gradient stepping large if the loss function is still large, and it automatically reduces the learning rate if and when the loss function becomes small. The derivative of each of these activation nonlinearities impact the gradient descent form in mitigating the update of the parameters. The task of supervised learning can be approached in a structured way using adaptive non-convex or convex optimization. This approach takes into account dynamic constraints within the network and ultimately results in a generalized form of the backpropagation algorithm.